Remember,
All right, welcome everyone. So I had a question. About midterm 3. So midterm 3 will be a week from Wednesday. So that will be your last midterm, and then your final will be optional retakes. I had another question. What if you do worse on the retakes? So I take the higher of whichever grade you get, whether it's your midterm grade or the retake grade. All right, any questions about any of that? Yes.
what day is the final?
Don't remember that one. So December 6th, it looks like will be the, oh, it doesn't say the time though.
10:30 to 12:30.
10:30 to 12:30, is that the final exam? Okay. Oh, sorry.
That's the bottom there, yeah.
I did write it down there. Okay, Thursday, December 14th. Goodness. So it follows the university schedule, and so that ends up being Thursday, December 14th, 10:30 to 12:30. Is there questions? Do you guys have any questions? Okay, you good? Okay, so Thursday, December 14th, 10:30 to 12:30. Okay, so final optional times, you can see there's only 2 hours in there. So if you opt to take all 3, it's a compressed time frame. So I'll reduce the need to do a lot of calculations typically, where it will be a little bit more focused, but all the same concepts as what was on the midterms. So in cases like was it exam 2 that I only gave you 1 problem? Or was it exam 1? Exam 1, you again will only have 1 problem to make it fair to be the same. So that one will probably be the least amount of time, where the others will probably still take you a little bit more time. So do plan accordingly. If you plan on taking all 3, take your one you want to make sure you spend the most time on first, and then go back and take the other ones. You can have them all open at the same time. So if you did want to say okay, I want to take a minute and go to another exam, you can open them up at the same time. The only thing is that it will start your timer once you have them open. So they'll still be timed for that 2-hour time period. All right, any other questions? Yes. Oh, what? Sorry.
The unit 3 review quiz.
Like the practice, yes. I was trying to do those over the weekend, but holidays distracted me too. So I will try to have those up by tonight. So we'll have that unit 3 practice exam again, which I do recommend going through. It will have, and especially if you keep going over it, it will have new problems each time. So, or similar problems each time. So you can have lots of practice. It will count for an extra, like it will replace a homework if you want it to. A student asked me, well, if I have great grades in my homework, but my quizzes haven't been so great, could it help me there? Typically, I don't change those grades, but if I have an option to bump you up slightly, like if you end up with like an 83.9, it's easy for me to use that extra credit as like a bump up to the next grade. So that fractional points, I can bump you up a half grade. And so I definitely suggest keep doing those practice problems too, because practice makes it even better. All right, any other questions? All right. Going back to our current lecture, I apologize. I did not get these notes posted, and so you will need to, I'll post them after class, but they won't be posted for today. So midterm 3 was already announced as being next week in Ingman or online. If you do it online, you have to join the remote meeting, and so that I can have you proctored still. So again, those that are online, if you do opt to take it online, make sure you join the Zoom meeting and do your exam or do your exam at the same time as we are taking class. Otherwise, you could get a 0 for the exam. Again, I'll iterate that again. Anybody taking that remotely, especially those that are online that may take it online again, you need to start the Zoom meeting at the same time as the class. And so you will have limited time just like the class does, but you do need to have that Zoom proctored. So make sure to join the Zoom meeting. All right, types of problems you're going to have. Oh, go ahead.
I just have a quick question. Is the make an exam assignment posted yet?
It should be. Anybody have theirs open, they can check. So your exam 3 group work, if somebody has their computer open, just check that it is off. Sorry. If you click on discussion, does it pop up on the discussion? No? Okay. I will make sure that that is posted by tonight too. And again, you'll have that same group work, or you can, again, do it individually. If you're a person who is like, I want to do it individually, that's fine. Just make sure to submit it individually by the due date, which will be the Tuesday night by midnight. So don't start it at 11 o'clock. You won't have enough time to get it done. Don't procrastinate that. And that will also be good practice, or hopefully that's the goal of it, is to be good practice to prepare for the exam 3. All right, any other questions? Okay. Problems themselves. So I would like you to understand what is the terminology and how do you calculate those terms. So average values, RMS values, complex power, apparent power, average power absorbed, reactive power, and power factor, including leading and lagging. So those are going to be similar to what was asked in the quiz and what was asked in the homework. Any questions on that content of what I expect you to know for that? Okay, good. Number 2 is to choose the load impedance so that the power dissipated in it is at a maximum and how much power that will be. So that's going to be a problem. And then to calculate the Thevenin. So we're going to go over the Thevenin again. So the Thevenin has to be calculated. From the Thevenin, you're going to get 2 values, the voltage and the impedance. The impedance you need to use to calculate the load impedance, which is going to be the complex conjugate of it. And then the power max is going to be the equation, so VTH squared, which is the magnitude of VTH, because VTH is complex, over 8 times the real portion of the load that you found. All right, so that will be the second type of problem. Any questions on what's expected for that type of problem? All right, third type is understanding what type of a filter. So being able to look at that Bode plot and understand, is it a band pass, band reject, low pass, or high pass filter? So that's being able to identify the kinds of filters it is. Understand bandwidth. So what does that term mean? If on the graph, how do you determine that value? The quality factor, which is Q, and the resonant frequency, and then the corner and cutoff frequencies. So those are all terminology, or being able to identify them if given a graph. Transfer function concept, what does it mean to have V out over V in? How to derive that if it is asked to derive it. And then what is a Bode plot? So those are things that you need to understand and know for that third type of concept, yes.
Are we going to do that from start to finish? Like,
No.
or would we be getting that?
So I'm not going to probably ask you to do derivations of the whole circuit, because I'm probably going to ask you to do that for the maximum power. So I'm going to see that you can do it. I may ask you, like, concept wise for about Bode plots. Like, what does this mean? You know, and looking at the Bode plot, how do you identify the corner frequencies or cutoff frequency or bandwidth? And what filter type is this Bode plot? Yes.
I'm probably losing my voice, so I apologize in advance. So how can we, from a circuit, tell what kind of filter we have?
That you have to first get the V out over V in transfer function, plot the transfer function Bode plot. And so right now, the only way you know how to do that is using MATLAB as that Bode plot function. So you have to have the control toolbox and plot that. Then from there, you can identify what kind of a filter it would be.
Yeah, thank you.
In 2280, you learn how to actually look at that equation and graph it by hand and be able to do it pretty quickly. So that's a technique you learn in 2280. All right, any other questions on that content? Okay, the last portion of the content is this Fourier analysis. So far all we've learned is how to apply the Fourier transfer technique to analyze the circuit with a non-periodic, kind of either non-periodic or a continuous function where we don't have t equals 0 defined, where we can use Laplace. So that's what we've done so far. And so part of that, you have to understand that Dirac delta function properties and being able to use that to solve for the Fourier inverse transfer function. We also use for that, again, going back to the partial fraction expansion method to be able to determine those values to transform it back. So those techniques are kind of the math behind what you need to know. Depending on what I can put together for Wednesday's lecture, we may go a little bit into the Fourier series and being able to draw like the line spectrum or understand that a little bit more. But it just depends on how much I get together for Wednesday. If so, that would also be part of the content of this next exam. But as of now, just ignore that first portion for A, B, and C. So we'll just do mostly D, which is analyzing the circuits, which you are comfortable with right now. This Thursday and Friday will be homework problems. You'll have probably a maximum power transfer problem in homework, and then also kind of questions about the filtering. And then the quiz will be, I haven't decided yet if it will be on one of those two topics. So based on the homework concepts, it will be on one of those. Most likely the maximum power transfer, since you haven't done as much problems with those. All right, any questions about content? Okay. I had a request to kind of write down the steps for some of these. And so Fourier transfer analysis is to solve the circuit. Usually I do an S domain, and then at the very end, just change into J omega, and then use the circuit techniques for node voltage is my usually one I go to obtain whatever variable you're trying to find in the circuit, and then do an inverse Fourier back to the time domain. And that was where I mentioned the math techniques. For maximum power transfer, you're going to find the VTH by placing an open between A and B where the load was. And then you're going to take ZTH by removing the independent sources and then take a path from A to B. And then Z load is just going to be the complex conjugate of ZTH. And Pmax is going to be the magnitude of VTH squared over 8 times the real portion of ZTH. So these are going to be the steps that you're going to want to do. All right, so we're going to start today with, before I start though, any other questions in general about anything that you've come across? Hopefully by now you've had time to watch the videos about the not say it for some reason, Dirac delta function. And so those derivations make more sense, and then also how to use them. Last time we had the circuit where we had already solved the equation for IC, and then you had the input of 10 plus 5 cosine 4t. And so from that, you needed to understand the properties of that delta function to then be able to solve that to get the end form in cosine form. So anybody have any questions about getting that one? Where do you want to start? Okay.
Maybe we can see an example at some point in that class, just doing that, helping with the direct delta function.
Okay.
If
So
that helps,
another example.
if that's helpful. Yeah.
Okay, I will try and work on one for, I don't have one prepared today, but I will get one ready for Wednesday. All right, any other? So this specific one has the video solution. So if you haven't watched it yet, definitely go make sure you watch that before Wednesday so that you're comfortable with that. The video before that is the delta function property descriptions and how the equations kind of come. You definitely, oh wait, what's up above? You definitely want to understand these functions and these properties of the delta function. So, is there questions? Okay. So just make sure you understand that the delta function, whenever you integrate it, it's going to have a value of 1. If you're multiplying the delta function by some other function, when you're right at 0, it can only be valid at that one location. So that is why the integration only ends up being with the value of f of 0. And then if it's shifted, it's only going to be the value right at A where it's shifted. So f of A will be that integration. So you can ignore the integration because the only thing that has is one value out of it. So that property is very essential to when you don't have a direct transform on the table. And you're going to have to use that for the integration. It is a lot more common to have functions that will not match up with the table for Fourier series. So understanding this property becomes more essential. I love the poor yucky look. So I went through the derivations in the video. So to understand where those kind of come through, I went into more detail in those videos. So do watch those if you haven't yet before Wednesday. And today, let's move then to this. So you want to choose the load impedance so that the power dissipated is at a maximum, and then calculate how much power that will be. So go ahead and break up into your small groups. You guys that are online, you guys can work together, or you can work individually if you prefer. You can use the chat window if you don't want to voice questions, or you're welcome to voice questions. All right. Go ahead and work on this, and I will cut and paste the steps again. So VS is needed. So VS is given, and it will be so it's already given, it will be given, it's given in polar form. So 10e to the j 45 degrees. And another way you'll sometimes see that, again, to be reminded, is 10 with this angle sign of 45 degrees.
Yeah, well, because it brings those two together. A is also in my heart. Most things that they do is straight to the school. Yeah, I think actually there's something wrong with like that. They might shoot. That's like this, like probably. It's more Easter eggs. When I did, he said, yes. You just said, and the next thing you know, they're gonna see that. Yeah. Also, that's Singapore. There's nothing we can say. Yeah. Yeah, I sort of got it. Yes. Chicken casserole.
So it's what you're not to change, only for our change, or we change that you remove the. So that's a sentence. So you need to change for the other or.
Yeah, so it's like. Oh, shelter. It's just like. Dude, I'm so sorry, man. You should tell Adrian. Adrian in the hospital. Yeah. Yeah, are you done? Word. Okay. So we did not involve people.
So.
Maybe. I wouldn't do it. And it's still.
Yes, oh, change.
That's, it's coming. It's coming. I spent, yes. I wanted to do it. Yes. Like.
Yeah, not right. Okay, sorry.
Oh, you have that. We finished it. We didn't have it. Yes.
Yes. Minus. I don't think so you got the A.
Like it was. Yeah, the entries were.
But it is.
You just have to, you just go. If you send it on level, it's.
Yeah.
Are you invalidating every claim? I think it's to be more. Because I think so. And, yeah. It's so. It's like, I'll be citizenship. You mean solve it, or like, yeah, just this. Well, what was your? You found that this now? It's honestly, because this is my greatest. Yeah. He was really nice.
Here on this side.
Yeah.
It's more than.
No, okay, do we agree with this? Yeah. Yeah, I did from terminal. So. Oh, yeah. It would, not, I know.
Yes.
Yes. Yes. Yep. I used to have it in series, but I think they're now terrible. But then I was just thinking, that's this one. Yeah, because I'm like, this is what the common plans is. That's the current one. It's what it comes down to. Well, yeah, but there's still. It was just on now I have this, and then I take this and I turn it. Where I have no. I don't have. That's the family. Well, consider like. I cannot serve. It's kind of like, yeah. I went back. Yeah, I'm just thinking now, it's like, hey, it's going on like rate. It should. That is very. See, I think better we could do well, I see how, I see how it's just. I'm just thinking, my mind, I don't see it in the text before. Because I see A. If it goes to the 8 on my street, it goes to I just think. No, I just what I understand using 24 as the great so we used to create. Because I was just too lazy. Stupid. This is the that work. They can just multiply that. Like, oh, wait, I just step back. So I am just gonna. Basically, I'm not sure if I did. I'm not sure if I sent this. So can you look at how I go? But that's like being there. You just have.
Maybe we should say, by a raise of hands, who has done the ZTH yet?
No, that's good.
Only a couple of people. Okay. No, you're fine. Let me come back to that when more people have worked on the ZTH. Yeah.
We did VTH.
You gotta figure out how to do it. Okay.
I'm saying he's still in her. You get the. And the thing I was saying, but I just ran it, and if so, assuming everything's correct. Would my answer be this thing? Oh, it is. Oh, that's right. It was the positive, negative, not This is what it looks like to me. Thank you. Oh, so you got yeah. I guess I did so this is how it looked like. Please laugh.
What's supposed to look like for Power Max?
2.2 milliwatts. So that'd be 2.3 milliwatts. Yep, that looks correct. Good job.
I actually my friend so maybe the road my friend is facing someone over there. See how it goes.
All right, so for ZTH, the first step is to remove the independent source. So for the independent source, that means that you're going to put V equals 0, which then puts that to a wire. And now if I color code kind of these, I've got green kind of that goes now all around with that short. And if this is red, blue, like that up there. So how I look at this is I do take a pathway from A to B. Whenever I have a split, means that there is going to be a parallel form. So A to B means that A is in parallel. So this will be, parallel with 6J. So from there, it then combines and you see you have green everywhere. So it goes to green. And then it is going to be a split again from the green to this. So because everything is green, that becomes an addition. And then 4 will be in parallel with a minus 5J. Yeah.
If I did, like 4 plus 6J is in parallel with 8 minus 5J, is that a close one? I wonder if it was parallel with 8.
It looks like it would probably come out to be the same. You'd have to calculate them, but I think that would be similar. From here, then you're going to take, you can do 1 over 8 plus 1 over 6J, or you can combine them with a common denominator for this form. Whichever form you get, or whichever, like 1 over 8 plus 1 over 6J, whichever form that you have, you just want to make sure that you end with rectangular form. So here, I would use Wolfram alpha to go from this to this step, or a calculator. So I could use MATLAB to simplify that to get this term too, or Wolfram, or my own calculator. Just make sure you do know how to use that, whatever you're going to use correctly. So you should end up with this. And then ZL is going to be the complex conjugate of this. So what will that be?
1.32 minus 1.9.
Correct. So this would be my ZL load. Jackson, did you have a question too? Oh, I thought I saw another hand. Oh, sorry, it was Ian.
This is really basic, but could you help me visualize the path of the current from the A going through the up arrow?
What do you mean?
Like,
Yes,
I don't know if you could, like trace, I don't think if that is, just.
Why couldn't you combine those two in series and then put, J6 and 4 in series and then parallel with 8 and -5 and 0? Is that how much of that? That's what you asked, and she had said that it would probably.
Yeah. I'll have to go look into that, but you probably could add those together. 4 plus 6J in parallel with and then add it to an 8 in parallel with minus 5j. I think that should end up being the same. It's just which one are you combining first, but I'll calculate those and let you know next time. And if not, an option Y. So I'll get back to you guys on that one. All right, any other questions? Yes.
My question is, I feel like on circuits like these, like usually when we like reduce the resistance, it's like, it's easy when you can just show them, like you can visualize it, you can show them together.
Mm-hmm.
I guess for these ones, it's just like, you have to see it split and you know how to set up the formula and then solve, or is there any way you can like do the parallel between imaginary 6 and 8 and like show the circuit after you do the parallel equation? Do you know what I'm talking, you know, when we're doing like the equivalent resistance circuits and you can just like reduce it down further and further until you get like it all together?
Yeah.
Is that even possible on these?
It's a little harder to see, so it'd look more like this. Let me see if I can draw it. So it kind of looked like this. So now that I've redrawn it, maybe I'm rethinking that you could add those together first. I think you have to have them in parallel.
Yeah, I don't.
4 and 6, yeah. Because this would be what it would look like. So the green is still here, and then your red. and blue. Does that help? And then you can see, like, yes, they would be added together, but they are in parallel with each other. But I don't know if you see, like, moving to that step
No, I
is a little bit harder visually. Okay. Yes.
Yeah, that's a good
So anyone want to answer that one?
question.
So when I put this at V equals 0, why is it a wire instead of an open? If I had an open, what would the voltage here be?
Infinite close.
Whatever's on the top.
So if this was X and Y, then this is going to be Vx minus Vy, which is not necessarily 0. Voltage of 0 is a wire. Current of 0 is when there's no way you can put current through the wire. So that's why you have it as open. I don't know if that helps. Okay. So voltage of 0 is going to always be a wire. All right. Other questions? I go back. Okay. Moving on to VTH. So VTH is going to be the voltage between A and B, which means that I can define VTH as VA minus VB. Oops. And then I need to find VA and find VB. So, you know me, node voltage. So VA minus VB over 6J plus VA over 8. And I'm going to define the bottom node as my ground. And then for the VB node, I have VB minus VS. Oh, sorry, this was VA minus VS over 6J. And then this is VB minus VS over 4 and VB over minus 5J. So now I have 3 equations and 3 unknowns. So I can either set this up into matrix form, set this up into MATLAB solution. I can go through by hand. As you've seen, I don't necessarily like hand, so Wolfram, or in this case, I typically like MATLAB. So using one of those or your calculator, you can get down to find that VTH should be 0.3. Okay, now I have a question mark by this, so I'm wondering if this is accurate. I'm gonna need to recheck this.
In MATLAB, you have to set up you have to, it will automatically transfer to the folder. You have to, in that.
You may need to manually do it. You got, yeah, I have a question mark by that, so I don't know. What angle did you get?
59.5.
Anybody else get the magnitude? What did you guys get? Did you guys get an answer? Not yet. Okay. Okay, I'm going to confirm this and I will correct these notes when I post them, and I'll send an announcement about what it should be. Because I forgot I had a question mark in my notes. So I think I might have had a little bit of an error there. I think the magnitude is correct. I think it's the angle that was wrong. I did it by hand, so I'm thinking that I might have made a mistake. Yes.
Is this the angle that's indicative of leading?
No, so this is not going to be the apparent power. This is going to be apparent power. Leading and lagging is only calculated if you know voltage and current.
Yes.
Going through this, we're only finding voltage here. So we haven't talked about the current. So you could find it once you found the current going through there for this particular input source. And then from there, you could find the leading and lagging from there. But you do need to know both voltage and current descriptions to find leading and lagging. Okay, so I will check this portion and get back to you guys. The power is going to be just from the magnitude of that, which is correct. And then what value do I use for? Is there some questions? I heard somebody. Do you guys have questions still? Okay, you guys are talking about the work. Okay. As far as the bottom, what value do we use for the real of what? Which is going to be what in this case? Correct. So we're going to use that 5.32. So you use the real portion of that load. So 5.32 will be the bottom, and then it's 2.29 or 2.3 milliwatts will be the maximum power there. Yes. And that's the definition for the power, is 1/8 VTH magnitude squared over the real portion of Z.
So it's always 1/8.
It's always 1/8.
What was this again?
What was what?
What was it?
The S was 10 EJ to the 45 degrees. There we go. Move that way so you can see better. All right. Any other questions on the steps here?
When we plug in VS into the node voltage, we do the full 10 e to the J 45. So would I just use the magnitude?
Correct.
Okay.
Yes. So you could change that to polar. I mean, from polar, you could change it to rectangular. And then, or you could keep it in So you're gonna have to change one or the other. Since you're multiplying, usually I change the rectangular to polar to multiply them together. Okay. All right, I told you that I wasn't gonna have you derive, but this one is a pretty easy derivation. So go ahead and find the transfer function for the following circuit. And then state what kind of a filter this is once I show you the graph of it. So plotting the Bode plot of this, it will look like this. Yeah, both inductors are the same value. So this is the Bode plot. Yeah, that's the Bode plot of this circuit. So from this Bode plot, identify what kind of a filter this is.
Can you zoom in on the values or? Yes, thank you. That would be.
Do you read them now? Okay.
That one.
Micro Henry, they're both micro. So 1 microhenry for the inductors and then 1 microfarad for the capacitor.
That's what we want to do.
Oh, Sorry. Oh, no, right. But E to the J, like that.
Oh, yeah, you do like EXP parentheses J.
Oh.
And make sure.
I'm trying to make it. Good idea.
That's what you got? Yes, we are. And then we do it.
Yeah, yeah, that.
Okay.
Yeah, I did.
They're-
These are done.
So I guess CS and.
Yeah.
I see, great motion that does that. Run to. I think so, yeah, maybe something was. Actually, just plug it down. Like this one.
Yeah.
So we're trying to find, so it's every node I would plug in the SL, right?
But we're really just kind of be out of the initiative.
Simplified. The good with this is what the transfer problem.
Yeah.
Symbolic.
But when you get into counts. Then you have to. Exactly. It's like. So that'll be. That'll be the. Yeah. And then. One.
Where it's.
No.
But that plugs into the exact right. That.
Okay, so. Meat paste, okay. VO, so I did VO node voltage, so VO minus VI over R plus LS plus VO over 1 over CS, and then plus VO over LS equals 0. So there's my node voltage equation. Then I combined all of the VO terms, took the VI over to the other side, and then got a common denominator here for these terms. And then I just took that over to the other side, so it flips the bottom up to the top. So it leaves R plus LS on the bottom, and then the R plus LS times LS goes over to the top portion. So these two then cancel. And I'm ended up with this equation. From there, to use MATLAB to graph it, I define my S variable is a transfer variable. So you do S equals TF of S. And then I put the R value L, C, and then I just typed in that equation. And then you do Bode magnitude of H of 2, and that will graph that Bode plot. So this is the graph of the Bode plot. So what filter type is this? Okay, band pass. And again, to identify what that is, you have to look at where 0 is on here. And so to determine the bandwidth, how do I determine the bandwidth here? Which is 0.7, so it's about 70%. And then in dB, 0.707, which is 1 over the square root of 2, this is volts per volt. This equals 3 dB. So when I see it in dB, all I have to do is either go down by 3 dB or up by 3 dB. So making an estimate here of a -3. And then where that intersects, is this a high Q or a low Q? Okay. So this would be considered a high Q value. It's very steep. Omega naught looks like, I guess it could even go like directly on this. So I'm going to make this a little easier. So this is what would be omega naught. It's going to be this value.
Yeah.
I can say it's approximately 10 to the 6th. RMS value. Mm-hmm. So remember, it's the 1 over square root of that magnitude.
Is it all? It's always.
Mm-hmm.
Okay.
So unless we have more than one cutoff, so if it's squared, it then doubles. So it ends up being 1/2, which ends up being 0.7 times 2, so 1.4. Or wait, sorry, 1 over 1 over, oh my goodness, 1/2. So it ends up being 0.5. Oh my goodness, that was, sorry. But anyway, okay, so Q factor is the middle number. Cutoff frequency, corner frequencies are what?
Plus or minus WC would be. Oh,
So these red lines.
yeah.
So those red lines are your cutoff frequencies. So these would be considered your cutoff frequencies. And bandwidth, so say this was, what do you think that one is? Estimate the left, the one on the left. So each one of these lines, remember with the semi-log, is going to be, so this will be 2 times 10 to the 5th, then 3 times 10 to the 5th, 4, 5, 6, 7. So this is about 8 times 10 to the 5th. And then on the right side, what is that approximately?
Well,
This one. Okay, so your bandwidth would then be the difference between those two. Or, sorry, 8 times 10 to the 5th. Whatever value that is. Okay. Questions? So make sure to understand those terms and then kind of how to identify them on the graphs. All right, I won't make you do the MATLAB portion of this. I would give you kind of the graph. But then I would want you to be able to identify what kind of filter and identify those terms in the filter. All right, any questions? Yes,
Would you want us to identify like our estimate for the bandwidth on the test?
I might. Or I'll give you specific values, but you might need to like extrapolate off. I'll probably be more specific so that it'll be easy to grade. But it would be like, it could be an easy graph, like, oh, it's really easy to see what that is. But do understand where it is so you can identify those locations. All right, any other questions? Yes. So a high Q is how wide your bandwidth is. So, so the more select it is for like, it goes up to almost a point is the high Q value. As you can kind of see in these different graphs, the green is a low Q where you're like, oh, it's hard to define where that range is and it's really wide. And then for each one, it's a little different. So like this one, you know, again, it like can slope up and it would be a low Q, and then a really sharp one, high selectivity, would be a high Q. Does that help? Okay. All right, have a great day.
You're not gonna make it. Fine.